This presentation assumes that many organizations are challenged with doing more, with less. Their future is based on recognizing this challenge, and responding to it in the most efficient manner. We suggest that there is an opportunity to benefit from CUMPSIM's Keil technology. Keil stands for Knowledge Enhanced Electronic Logic. In this new world, there are new adversaries, each with their own new, and ever-changing, strategies and tactics. Commercial technology is being developed and distributed at an ever-increasing rate, and that technology is immediately available to friends and adversaries alike. And small entities can often make use of that new technology more rapidly than large organizations with built-in inertia. New technology is being introduced in miniaturized, lower-cost packages. Organizations and individuals that were previously blocked, due to cost constraints, can now enable themselves of the latest advances. The Internet has shrunk the world, so new technology-based products can be acquired and delivered anywhere. Only agile organizations that embrace change can hope to survive. And the concept of Internet time highlights that the rate of change is accelerating. So the challenge is there. Organizations have to do more to survive and flourish. To make the problems more difficult, there are budget and time to market constraints. If the problems are approached the same old way, then one quickly realizes that systems will fail. It is not possible to simply add more people to address the challenges, when people cost money. And humans performing tasks the same old way, will be too slow and make too many mistakes. And those mistakes also cost more money. Historically, we have built machines for automation. The term automation can simply be defined as a process that can operate automatically. Whether the machines are built to increase speed, to increase accuracy, or to carry heavier loads, they have been built to amplify human capabilities. In other cases, we have built machines to keep humans out of harm's way, and in others, to place humans in areas where humans cannot go. In manufacturing, we are attempting to take humans out of the main control loop, so we can make more products faster, and operate automatically. In the information domain, we have computers that amplify the human's ability to process information. With programmed machines, we still have humans controlling the behavior of the machines. So we still have humans on the loop controlling that behavior. But with all these advances, there still remains more opportunities to improve. It is clear that there is a recognition of the problem. Perhaps it is clear that there is a recognition of the many opportunities that are awaiting solutions. There are many, very many, requests for new algorithms to solve the obvious, and not so obvious problems, by many organizations that have recognized they have problems that they will have to address. This search for algorithms suggests a conventional way of looking at the problem space. The subject matter expert has a general idea of the problem. The SME may generate a conceptual statement of the desired solution. This may take the form of a request for a new algorithm. Potentially, the group that identifies the problem has some need that needs to be addressed, and some funds to pay for the research. If the research group has the resources, maybe some staff mathematicians, they may attempt to develop a formula that would satisfy the algorithm requirements. The formula may be handed off to a software engineer to develop a program that translates the formula into computer code. The code will likely have to be placed in some kind of simulation environment, so the group with the problem can determine if it satisfies the need. If not, then back to the drawing board. If it does, then the code may have to be regenerated into the language and form factor of the production environment. Only then can the solution produce the automation desired. And if something goes wrong, there is likely a group effort by the software team, the mathematicians, and the SME to reverse engineer the production code to understand what happened. It is assumed that the algorithm correctly responds to the specific problem to be addressed. There is an expectation by the group funding the development, that the algorithm request correctly define the problem. This process has been in place for years, and has led us to where we are today. Manufacturing automation systems have well-bounded environments, and the algorithms, or programs that control the machines, provide the automation. But we still need more. And the problems that need solving may not be so well defined. There is the entire domain of autonomy, autonomous systems, self-driving cars, drones, software agents that can hypothetically address many of the problems that remain to be automated. Perhaps there is a new way to look at the problem space. When we are dealing with humans, and have a desire to direct those humans to perform in appropriate ways, we create policies to direct their behavior. The policies, or guidelines, do not specifically address every detailed attribute of the problem space, because if they tried to be that specific, the humans would never be able to understand them, or find the specific match to the task they were to perform. So policies and guidelines attempt, in general terms, to tell the humans how to think, and how to act. Perhaps this approach could be applied to machines. Perhaps it could provide the necessary methodology to address many of the complex problems that remain to be automated. This is what we suggest is possible with Keel technology. So with Keel we are defining how a machine is to interpret information and react. When we talk about autonomous systems, or the need to automate human processes that have benefited from human operational expertise, or human problem-solving expertise, we are talking about systems that solve problems using judgment and reasoning. By looking at the term behavior, rather than the creation of an algorithm, we enable the SME to focus on a broader, less well-defined problem space. With Keel technology we are suggesting that the SME, that has hopefully the best understanding of the problem space, can actually create and test the desired behavior without depending on the mathematician or software engineer for the development work. Only when there is a desire to package a working solution for simulation or production, is there a need to move the model to code. And the conventional code is auto-generated by Keel tools. With Keel technology, we are also addressing the need, with these more complex systems, that is to audit their behavior. When we have humans performing complex tasks, and systems fail, we don't expect the humans to explain, with mathematical precision, what went wrong. We just accept that they are human. Such will not be the case with mass-produced machines. So Keel technology has capabilities specifically included, to make it easy to reverse engineer complex decisions. The concept of after-mission reviews come into play here. In order to differentiate between creating an algorithm and creating a policy to control behavior, perhaps this view might help. With an algorithm, one is attempting to solve a specific problem. With an algorithm one is expecting a correct answer. This maps well with how computers process information. They sequentially process if-then-else rules. They do this very fast. We might call this left brain processing. When we talk about behavior, we are talking about how an entity will think and react, rather than how it will solve specific problems. We want to tell it how to apply judgment and reasoning in order to dispense packaged expertise. So we want to tell it how to interpret information, that will in turn, allow it to adapt to situations it has never been specifically programmed to respond to. And when we talk about behavior, we are often asking our entities to address multiple goals simultaneously, just as we challenge humans to behave. When we may give them multiple goals, some of them may be conflicting, and they may have to allocate their resources across multiple domains. Examples might include the need for refueling or maintenance, self-preservation, providing assistance to others, pursuing assigned goals, responding to new opportunities and new threats, all while considering legal and ethical directives. We might call this right brain processing. So revisiting the problem of doing more with less. Much of what has already been automated has been accomplished with conventional processes. While some might reject the suggestion that all of the problems that have already been addressed, have been easy, we might suggest that those that still demand humans in the loop to provide the necessary expertise, are more complex. We are dealing with information that is changing in importance as the situation changes. Information has to be interpreted in nonlinear ways and include temporal aspects. Pieces of information will be treated differently in the evaluation and prioritization of different goals. The behavior of our systems will have to process information collectively, to obtain the best overall behavior. These are the capabilities that have required humans in the loop in the past. To do more with less, means, in many cases, that we want to automate the delivery of human expertise. This could be for the human expert's decision-making ability, or it could be for operational control. So to deliver expertise, means that we want to package the expert's judgment and reasoning skills in order to allow our system to pursue its multiple goals in a mathematically explicit manner. We will have to package a value system, because for our system to balance alternatives it will have to use that value system to interpret the importance of information and the importance of influencing factors. We will have to be able to tell our system how to adapt to change. And we will have to have solutions that are easily auditable and traceable, as well as systems that can easily be extended and fixed when necessary. This is what we are offering with Keel technology. No technology will be successful if it is not easy to use. Keel, with its dynamic graphical language, makes it easy for an SME to capture and test the desired behavior, without dependence on mathematicians and software engineers. The Keil dynamic graphical language makes it easy to model adaptive behaviors and address problem sets that have dynamic, nonlinear, interrelated, multidimensional attributes. The interactive nature of the Keil dynamic graphical language allows the models to be tested while they are being developed, before committing to conventional code. A concept called language animation addresses the need for auditability and traceability after policies have been packaged for simulation and/or production. And when the design is complete, the conventional code is auto-generated for delivery to the software engineer, so it can be inserted into the target platform. Continuing with the easy topic. It is easy to insert the auto-generated Keil engine into new or existing applications. Keil engines are software components, with a simple API, that can be inserted into any platform or any system architecture. With a concept called design once, deploy many, a single Keil-based policy could be deployed on multiple production platforms, training systems, demonstration platforms, different simulation environments, all with just the click of a menu option for regeneration of the model in a different computer language. Keil engines are optimized for deployment in small embedded real-time systems. This makes it easy to insert judgment and reasoning skills into small autonomous devices. The Keil engines are self-contained. This means they are not dependent on additional libraries that may not be available for all platforms. And finally, the Keil dynamic graphical language is easy to learn and does not have any prerequisite skills in mathematics or software engineering. All it takes is subject matter expertise and an interest in packaging that expertise for deployment in a device or software application. If you consider what has been accomplished with left-brain computing and if-then-else programming concepts over the last 100 years, think of the opportunities for doing more with less, using right-brain computing. Keil technology is available now, to satisfy the need to do more with less, and to package expert-like behavior into software applications and devices.